right, today we're going to look at the probability of compound events. This should be our last day of notes for Unit 8. We'll just be reviewing after this. So it says, recall if you see the word and, then you will multiply. If you see the word or, we will add. Suppose 10 red marbles, 12 blue marbles, 8 green marbles, and 4 yellow marbles are placed in a bag and selected at random. Find each probability. So here we aren't using and at all. We'll get to that in the next two problems. We just have the probability of a blue marble. So we take the number of blue, 12, out of the total. Let's see, we have a 10, a 12, an 8, and a 4. So 22, 34. 34 total. So if I take 12 blue and divide by the total of 34, this can reduce. They both are even numbers. Divide by 2, we get 6/17. To review complements, if I want the probability of not green, I could take 1 minus the probability that it is green. And there are 8 green, so there's 8 out of 34 green. If I subtract that from 1, I get, let's see, 34 minus 8 would be 26 out of 34. And once again, these are both even. If I divide by 2, that reduces to 13/17. For part C, I'm running a little low on space here, but I have the probability of blue or red. So I'm going to add the probability of blue, which there are 12 blue out of 34, with the probability of red. There are 10 red out of 34. And then I always need to subtract the probability of both. But if you think about it here, are there any marbles that are both red and blue? No, they're either one or the other. So really when I subtract, there's nothing to subtract there. I could subtract 0. So 12 plus 10 is 22 out of 34. And that reduces to 11/17. All right, last part here is the probability of green or blue. Why don't you pause and try this one, and then go ahead and hit play to check it. All right, let's see how you did on part D. So the probability of green would be 8 out of 34, plus the probability of blue, 12 out of 34, minus 0, because there's no marbles that are green and blue. And when I add here, I get 20 out of 34, which reduces to 10/17. So this is just review in number 1 of just finding a basic probability from an experiment, finding a complement in part B, and using the or the addition rule from last week. All right, moving on to number 2. Suppose a die is rolled and a coin is tossed. What is the probability that an odd number is rolled and the coin lands tails up? So we want probability of an odd number on the die and tails on our coin. So up above it says that if we see the word and, we're multiplying. So we're going to take the probability of a die landing on an odd, and we're going to take the probability of a coin landing on tails, and we're going to multiply those two probabilities together. So for the probability of odd, that would be 1/2. And for the probability of tails, that's also 1/2. When you multiply 1/2 times 1/2, you get 1/4. Now for a die, I could have also thought of it as 3 out of 6, but I reduced it to 1/2 right away. If I had 3 over 6, then this would be 3 over 12, which reduces to 1/4. So when you see the word and, you're finding each probability and multiplying them together. Let's look at number 3. 2 cards are drawn from a standard 52 card deck without replacement. Without replacement means you pick a card and you don't replace it or put it back when you pick your second card. So what is the probability of getting a king and then an ace? So if I want the probability of a king and an ace, I have to start with the probability of a king. That's 4 out of 52. We have 4 kings in a deck out of 52 cards. And means I'm going to multiply. Now I want the probability of an ace. You have to be really careful here because there's 2 different answers depending on this, because it says without replacement, we are assuming that we already picked a king. So there are 4 aces left, but there's only 51 cards remaining. So what would be different here if it said with replacement is then that king would have been put back, and we would have a 4 out of 52 chance of getting an ace next because we'd have all 52 cards to pick from again. But if we're not replacing that first card of a king, now there's only 51 cards remaining when you're calculating that second probability. So here is where we need to get out calculators because these numbers are getting pretty big. First of all, when you're multiplying fractions, you multiply the numerators together and the denominators together. So in the numerators, 4 times 4 is 16. In the denominator, 52 times 51 is 2,652. And if you use your calculator to reduce by dividing, pressing the math button, and then converting to a fraction, this reduces to 4 over 663. All right, what I'm most concerned about is your work, which is this. So please don't just put down final answers. Please show me what you're multiplying, and then if you multiply it and reduce it, great. But I really want to see that work so I know you understand what you're doing. All right, so how is number 2 and number 3 different from each other? In one of these, we had independent events, and in the other, we had dependent events. In number 2, when you're flipping a coin and rolling a die, whether the coin lands on heads or tails, does that have any influence on what number the die lands on? No, and vice versa. Whatever the die lands on doesn't affect at all what the coin lands on. So in number 2, we call these events independent, and this is when one event does not affect the outcome of another. So I'm going to put number 2 next to it. Since rolling a die and flipping a coin, they have no outcome or no effect on each other's outcomes. Now, if the outcome of one event does affect the outcome, then the events are dependent. We saw that in number 3 because the probability of getting an ace on the second pick depends on whether or not you had an ace on the first pick. So, for example, if I picked an ace and then another ace, then I'd only have 3 aces left. But we're saying that we first picked a king, but then our denominator does change. Where if it was independent, that would only happen if I did replace the card, and then I would have a 4 out of 52, like I mentioned earlier. So we'll see more examples of both of these as we move through our notes. Let's look at example 1. Here we're talking about marbles being drawn from a bag without replacement. So I'm picking a marble. I'm not putting it back in when I pick out another marble. The bag has 4 green, 5 red, and 3 blue. So 4 plus 5 plus 3 is 12 total. Is this independent or dependent? All right, if it's without replacement, then when you're finding the probability of the second marble being a certain color, it all depends on the first one. So this is definitely dependent because we're not replacing the marble after each pick. So what's probably I get 2 red. I want the probability of a red and another red. So and means I'm multiplying. What's the probability of the first marble's red? Well, we have 5 red out of our total of 12. And means I'm going to multiply. And now the probability of the next one being red, I am finding that based on the fact that the first one is red. So if the first one's red, you have to imagine now that one of those red marbles is gone and there's only 4 left. Out of, once again, one of the 12 marbles is gone, so there's only 11 left. So if you're finding red and red, like the exact same event, in that second fraction, basically the number on top and on the bottom each went 1 lower. That's the important part. That's your work. That's what I definitely want you to show. If you multiply 5 times 4, you get 20. If you multiply 12 times 11, you get 132. And this can reduce to 5 over 33. Remember, we're finding probabilities, so all our answers should be between 0 and 1. Part C says, what's the probability of drawing a green and then a blue? So we want the probability of a green and then the next one being a blue, given the first one is green. So to find a green first, on the first pick, there's 4 green out of 12. Now to find the probability of a blue, if the first one is green, then we still have all 3 blue marbles left in the bag, but there's only 11 to choose from. Okay, so 4 times 3 is 12, and 12 times 11 is 132. And in this problem, it reduces to 1/11. Now here it's just a coincidence that the 3 is 1 less than the 4, because these were 2 completely different colors. Where up above I said this was 1 less because they were the same color and now one of those is gone. But here it's just because of how the numbers worked out, that this was a 4 and this was a 3. All right, moving on to example 2. A card is drawn from a standard 52 card deck and then replaced. So in example 1 we said without replacement, but in example 2 now we have with replacement. That means that now these are going to be independent events, because it won't matter what I pick the first time. If I'm putting it back, then I have just as likely of a chance to pick anything the second time, because the first one doesn't affect the second one at all. All right, we're not talking about marbles anymore, we're talking about cards. So what's the probability of 2 aces? All right, so on an ace and another ace. I'm supposed to say and. Sorry for my sloppy handwriting. So the first ace is 4 out of 52. Now, if this was with replacement, I would only have 3 left out of 51. If it was without, but it is with replacement. So that ace is going back in the deck and it's getting reshuffled, and now I'm finding the probability of another ace, which is the same, 4 out of 52, because I have all 52 cards still in the deck. So that's the important part of the problem, that you know you're doing 4 over 52 times 4 over 52. If you get out your calculator and multiply, this would be 16 over 2,704. That reduces to 1 over 169. Pretty unlikely, less than 1% chance that you're going to pick an ace and then another ace out of all 52 cards. All right, example 3 says 3 cards are drawn from a standard 52 card deck without replacement. Find each probability. So without replacement means it is going to depend each time on what the previous cards were picked to be. So we're going to be changing our denominator each time and going down by 1. So the probability of getting an ace is 4 out of 52. Now, given an ace is gone, there's only 51 cards remaining. What's the probability of a king? Well, there's 4 kings out of those 51 cards. Finally, what's the probability of another ace? Well, there's only 50 cards left because I've picked an ace and a king already. If I've already picked 1 ace, now there's only 3 aces remaining. So here's the work where basically you're using ace and then a king and then an ace. So we're multiplying, but we have 3 events this time instead of just 2. And once again, these are dependent because we're not replacing the card each time. So the probability of getting like that last ace here is found based on knowing we've already picked a king and then an ace. So let's see, 4 times 4 times 3 is 48. 52 times 51 times 50 is 132,600. And this can reduce to 2 over 5,525. If you don't have a calculator, make sure you're at least doing this work. This is the important part. All right, part B is the probability of getting a spade, then a diamond, then a heart. So out of 52 cards, there are 13 cards that are spade. If I've picked a spade, 1 card is gone and there's only 51 left, but there's still 13 diamonds remaining. If I've picked a spade and then a diamond, now there's only 50 cards left, but there's still 13 hearts remaining. So every single time I have 13 on top, but my denominator changes from 52 to 51 to 50. All right, there's the work for part B. If you do the math here, we have 2,197 over 132,600. And I don't think that reduces. All right. If you want to go ahead and pause and try part C, go for it. If you're struggling and want to see one more example, then that's fine. But if you want to give it a shot, go ahead and hit pause and then hit play to see how you did. So for part C, if I have the probability of a 10 and then a 10 and then a 10. there are 4 10s out of all 52 cards. But if I pick a first card that is 10, what's probably getting another 10? Well, there's only 3 left now out of 51 cards remaining. Now, what's probably of a third 10? Well, there's only 50 cards remaining, and if you've picked 2 10s already, like let's say the diamond and the spade, there's only the heart and club left, which is 2 remaining. So this would be 4 over 52 times 3 over 51 times 2 over 50. If I do the math here, on top I get 24. The bottom, notice it's the same in all 3 of these problems, and I don't believe that reduces either. So you could leave it as a fraction, you can convert it to a decimal, percentage, any of those are fine for probabilities. All right, one example to go here. In our last example, we're talking about a bag of slips of paper with numbers 1 through 10. If you select 2 slips of paper, what is the probability of getting an even number and then an odd number? And we're going to find that with and without replacement. So I'm going to write out these numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Even numbers are 2, 4, 6, 8, 10. So there's 5 of those. Odd numbers are 1, 3, 5, 7, 9. So there's 5 of those. So what's the probability of getting an even number and then an odd number? I'm not going to reduce until the very end. So if I want probability of even and odd, I'm going to start with probability of an even. There's 5 out of 10. Then I also want the probability of an odd, given the first card is even. Now if it's with replacement, it doesn't matter what the first card was, because I'm putting it back. So now to find the probability of odd, it's just the probability of odd, 5 out of 10. The first outcome makes no difference because I put that card back. Where in the next problem, when I find even and odd, same problem. The only difference is without replacement, after my probability of even, 5 out of 10, now the probability of getting an odd, there's 5 odds out of 9 remaining, because that first even card that I picked, I'm not replacing. I'm keeping it out of the slips of paper when I pick the second card. So now you can see back to back what the difference is here with and without replacement. So this would be 25 out of 100, which is 1/4. And in part B, we'd have 25 over 90, which these can both divide by 5, and we get 5/18. All right, we're going to do one final example here. Part C and D kind of go together. We want the probability of 2 even numbers with and without replacement. So I want the probability of an even and another even. So an even, 2, 4, 6, 8, 10. There's 5 out of 10 ways of doing that. So the first one, probability of just an even, is 5 out of 10. Now, if I replace it and put it back, then the chance of getting the next one being even is the same thing, 5 out of 10. But if I don't replace it, now I only have 4 evens left out of 9 because I picked an even already and I didn't put it back. So there's only 4 evens left out of 9 cards left. So when I multiply in part C, I get 25 hundredths, which is 1/4. And in part D, I get 20 over 90, which reduces to 2/9. Notice the difference between C and D compared to A and B. In A and B, I had even and odd, 2 different events, where in C and D, I had even and even, where these were actually the same event. And then the differences between A and B and C and D are, of course, the with and without replacement. That concludes the notes for today. Feel free to go back and re-watch any of these examples again if you still are struggling a little bit, and then go ahead and try the homework. All right, thank you.